In the late 18th century, a Scottish chemist working in Bathgate was observing the experiment he had set up. Coal was heated in a retort with absence of air to achieve destructive distillation. This process would break down coal into its simplest form, revealing the treasures within. With this, James Young had officially discovered hydrocarbons, thus setting off the next stage of our industrial revolution and marking us as a petroleum-dependent society. But way before even Scotland had become a nation, our ancestors were using hydrocarbons, such as bitumen, to waterproof their seafaring vessels, as an adhesive and to build their roads. 5,000 years later, it can still be found in the same purpose long ago. The very asphalt our cars drive on, the ships we sail, and the electric cables we use, all require bitumen in their production. This is merely one hydrocarbon. There are thousands more that provide a plethora of essential uses, and without them, we may never have become the modernized species we are now. But as a chemist, let us look at this from a chemistry view. Hydrocarbons in their simplest form are carbon and hydrogen molecules in a covalent bond with each other, with each carbon at its center bonding with other carbons and hydrogen atoms. It creates a stable structure. The simplest hydrocarbon is methane, CH4, a single carbon surrounded by single bonds of 4 hydrogen. This colorless and odorless gas is produced through natural processes such as decaying matter and digestion in animals such as cows. Methane is a potent greenhouse gas contributing to global warming and climate change when released into the atmosphere. However, it also serves as a valuable energy source when captured and utilized effectively, for example in heating homes and generating electricity.
In my hand is a lighter. It's used to light fires, and through a process known as combustion, this can happen. See, when combustion happens, it requires a hydrocarbon and an oxygen molecule to allow the reaction to create carbon dioxide and water. Since combustion, and technically most fires, requires a hydrocarbon, human civilization could not exist without it. This lighter in my hand here is filled with butane.
I didn't know you knew that.
Butane, C4H10, along with methane, are alkanes. Alkanes are non-polar molecules, which results in low melting and boiling points. Since the bonds between the carbon itself and hydrogen are quite strong, they are quite unreactive, but still undergo combustion, like seen earlier. Naming and notation for alkanes are quite simple. Simply multiply the number of carbon by 2, then add 2 to find the amount of hydrogen for your notation. For the names, use the prefixes with ANE at the end. Of course, more complex structures are formed, such as alkenes. These have less hydrogen because carbon wanted to get a bit more intimate with itself and double bonded with itself. Since self-love is quite dangerous unless you're a noble gas in chemistry, they are more unstable than alkenes mentioned above, with even lower boiling points. At this point, polymerization begins to occur, where monomers of these alkenes start bonding with other compounds, creating plastics, synthetic fibers, and many other things used in daily life. To notate and name these alkenes, multiply the carbon by 2 to find the hydrogen. Use this naming convention, but with ENE instead. This works for all except methane, because it doesn't exist. There are no double bonds. A bit more complex are alkynes. These carbons have triple bonds in their molecular structure. It makes colorless gases and volatile liquids that have even lower boiling points than before. These have a great variety of chemical reactions, being able to undergo hydrogenation, halogenation, hydration, and reductions to form different compounds. The most common usage of this are in welding torches due to alkynes' very high flame temperature. The naming conventions are still quite consistent. We multiply the carbon by 2, then minus 2 to find the hydrogens for alkynes. We name these with the scheme set before, but with YNE placed at the end. The exception is still methine, because it still doesn't exist. Diving deeper into the sea of hydrocarbons, more complex structures begin to form. Aromatic hydrocarbons with benzene rings allow for greater stability and more consistent reactivity. Cycloalkanes that force their alkynes into rings, which increases boiling point. Polycyclics, halogenated and functionalized hydrocarbons, of which the complexity would require its own subject and documentary. Now, hydrocarbons are organic compounds, and as previously mentioned, they are formed through natural processes. They originate from living organisms which have died, meaning yes, in a few million years' times, you too could be a vat of oil. When these organisms die, they sink to bottoms of oceans, lakes, or swamps. Over time, layers of organic material accumulate. This exerts pressure on the lower layers, and heat from the Earth core come together to transform organic matter into hydrocarbon through a process called diagenesis. Diagenesis is quite complex, so I'm going to break it down. It begins with decomposition. Bacteria and other reactions break down the organic molecules into simpler compounds. Catagenesis begins as the temperatures and pressure increase the deeper it goes, forcing hydrocarbon chains to become even simpler and letting go of their oxygen, nitrogen and sulfur compounds. At the bottom, deep into the earth crust, metagenesis begins to occur, where whatever is left undergoes thermal cracking and results in crude oil and other important natural gases. After diagenesis, these hydrocarbons can travel through the more porous rock and through cracks or folds in the earth crust, creating reservoirs. Since hydrocarbons are such a pillar of society and is so vital that it is sometimes called black gold, thousands of techniques, companies and people are given to the task to get it out the ground. Geologists use seismic surveys, imagery from satellites and other unique techniques to find potential reserves under the ground. Once found, we must now go get it. Massive drilling rigs are set up plunging into the rock. Once it has reached, pressure from the oil may be enough to bring it to the surface, but pumps are often required. These are often transported via pipeline, trucks, trains and ships to refinery centres. Here at Reliance Yamnagar refinery complex in India, it is one of the largest refineries in the world. Over 1.2 million barrels of oil and other related products is produced out of this complex. Crude oil is first brought through a process of distillation. Crude oil is heated and shot up through the distillation towers, where it cools at different temperatures. It allows us to separate carbons into different mixes such as gasoline, diesel, kerosene and heavy fuels. To refine the distillation process even more, it is brought through a process of fractional distillation where we separate out specific products. Gasoline may be brought through a reformer to increase the formation of octane, while diesel is put through a process of hydrodesulfurization to remove its impurities. Heavy fuels and residual oil aren't valuable on its own and are put through differing processes such as cracking and coking to break them into more useful products. Many refining processes include treatment, where the products are treated to remove impurities from contaminants such as sulfur, nitrogen and other substances. Lastly, many products are then blended together to meet different standards and consumer needs. This can happen at the refinery or the location of the sale. What can we do with all this refined variants of hydrocarbon? Energy generation is one of the most popular usages. Oil power plants use hydrocarbons to create steam to turn massive turbines producing electricity. They're used as transportation fuels for cars, trains, planes, ships, and other internal combustion engines. They have industrial applications, being used to make plastics, polymers, and solvents seen all around us. They are manufactured into synthetic fibers, lubricants, and pharmaceuticals. As a product we use so much and is so important, there are of course many massive trade-offs. We learn that in combustion, carbon dioxide is produced. All that carbon dioxide must go somewhere, usually into the air, causing dangerous effects such as climate change, smog, acid rain, respiratory issues, and other health issues. When carbon dioxide comes into contact with the ocean, it engages in a process of ocean acidification, harming marine ecosystems, coral reefs, and biodiversity. The process of drilling and fracking for oil leads to habitat destruction, water pollution, soil contamination, and even induced earthquakes. Plastics, a refined hydrocarbon, is its own terror, with microplastics being dumped into our oceans, finding our way back to us. On April 20, 2010, the Gulf of Mexico was met with an explosion. The Deepwater Horizon oil spill had just happened. A blowout happened while drilling, causing the immense pressure and temperature of the oil well to expand rapidly, lighting fires upon the rig. The rig sunk soon after, leading to a release of crude oil from the wellhead on the seabed. The spill was the largest marine oil spill in history, releasing an estimated 4.9 million barrels or 210 million gallons of crude oil into the Gulf over a period of 87 days until the well was capped on July 15, 2010. The spill had devastating environmental, economic, and social impacts, affecting marine life, the coastal ecosystem, fishing industries, tourism, and the livelihoods of communities along the Gulf Coast. Efforts to contain and clean up the spills involve the deployment of various techniques, including dispersants, controlled burns, mechanical skimming, and the construction of barriers and containment systems. The response and clean-up efforts were massive and prolonged, including government agencies, BP, the oil rig that fell, and numerous contractors. In conclusion, hydrocarbons represent the backbone of organic chemistry, embodying the fundamental building blocks of countless molecules that shape our world. From simple methane to the complexity in aromatic compounds, hydrocarbons exhibit a remarkable diversity of structures and properties that underpin their wide range applications in industry, medicine, agriculture, and other sectors. As we continue to explore the mysteries of hydrocarbons and harness their potential for innovation and discovery, we should remain mindful of our responsibility to these resources and preserve the balance of nature, ensuring a sustainable future for generations to come.